Oh, welcome back. Well, I'm sure you're all familiar what day it is. This is, in fact, March 14th. What is that? That is 3/14. It is not simply just a numerically significant day because of the symbolic gesture to pi. It is actually a very special day for more than one reason. In fact, it is Albert Einstein's birthday, and we are going to be honoring him by deriving his most famous equation of all time. And even the most uneducated layperson is familiar with this equation, maybe to a very superficial degree, because it is in fact incomplete, and not very many people are very aware of its entirety. And that is what we're going to be going through today. And we're not going to be invoking certain concepts like relativistic mass, which tends to be a little bit of a cop-out, if I'm being perfectly honest. I generally try to steer away from that because a lot of textbooks will lead you astray when you're sort of coming up with these ideas to make the reader a little more comfortable with these very just diverging ideas from the norm, at least from a Newtonian standpoint. So we're going to be starting with momentum and then working our way up, and we'll get there piece by piece. But first, we're going to have to go into several very elaborate thought experiments. So let's begin. So bring your attention over to this side, and you'll see that we have a particular frame of reference. And this frame of reference is representing an elastic collision. And from the Newtonian standpoint, and pretty much in all of physics, you have to uphold a certain standard when you're considering momentum, and that's the conservation of linear momentum. Not angular for this particular purpose, but it's not really that big of a deal in the grand scheme of things because we're not considering angular momentum. So for this particular idea, we have to uphold a certain sacred tenet of physics, and that is conservation. And even when you kind of delve into the relativistic side of things, that still needs to be upheld. So that is what we're going to be trying to analyze and express as to why there ends up being inevitable contradictions when you try to incorporate the Lorentz transformations that we went over in the last video. And we're going to be deriving a few key ideas along the way. So cast your mind 10 million light years away in a galaxy far, far away, and we have ourselves a supernova explosion whereby a proton within that explosion ejects at relativistic speeds far greater than any accelerator that we have here on Earth, because as we all know, the ability for nature to generate accelerators is far more efficient than we are ever going to be capable of, maybe. But for that idea, we have a proton that is reaching so close to the speed of light that it is reaching its destination that we're going to be looking at in essentially from its wristwatch time 1 second from its proper time. And that is going to be another focal point of this entire video that we're going to be kind of honing in on to understand why there needs to be a correction when you account for these just different frames of reference whereby one is moving at relativistic speeds to another. All right, so that is what we have here. The longer vector represents a fast-moving proton 10 million light years away, moving at close to almost the speed of light, such that it reaches its collision point at, from its perspective, 1 second. Now, on Earth, we have our lattice work set up such that we can detect this incoming proton up to such a precise degree that up to the moment that it reaches a particular point within the Earth's proximity, the stationary Earthbound observers emit a proton of their own that is almost perpendicular to the proton moving fast from the supernova explosion. And that way we can analyze a slow-moving frame and a fast-moving frame and see how this relates to momentum conservation. So we have this collision, and the proton being ejected from Earth is moving very slowly. In fact, it is moving 1 meter per second over a distance of 1 meter, and that is what we're going to be looking at for that particular frame here. Now, if we want to look at this particular collision, an elastic collision, well, from a Newtonian standpoint, we need to account for the change in direction due to its elastic collision, right? And to account for that, we are going to be adding this negative to indicate the shift in spatial directions. Now, if we were to just analyze the slow-moving proton, the Newtonian standpoint is all consistent, as you can see here. So the change in momentum within the slow-moving frame, well, we can just represent that like so. So we're going to have delta p sub 2 to represent our event that was moving slow, is moving slow here. So delta p is going to be equal to minus mv sub 2 in its final state, right? Because final minus initial, but it's negative because, as you can see here, it changes directions. We have to account for that with a negative sign. So we're going to be subtracting from our initial. We're going to have minus mv sub 2 initial, right? And if we just take the magnitude and we look at the total change in momentum here, well, the magnitude will just give us equal to 2mv2, right? That's great. That's all consistent with our ideas in the Newtonian perspective. We're not going to have any contradictions there. What we run into as an issue is when we start considering this fast-moving frame, because we have to consider a measured time at the Earth frame, right? Because in the Earth frame, we've measured its distance and the time it took to reach its destination, which was 10 million light years, or 10 million years in that particular sort of setup, right? So what we first need to look at is the velocity transformations that you naturally need to include, because I haven't obviously derived those. I looked at the position and time when considering any of the Lorentz transformations. And the velocity addition is actually fairly easy. But what you run into is when you consider these velocity transformations, when you're trying to move between frames of reference, and the contradiction that arises is conservation does not appear to be conserved when only looking at the transformation with respect to the velocities that we're accounting for. So, for instance, if we were to just take the position transformation and the time transformation, this can be derived very easily. So we're going to have x prime equals gamma times x minus ut. And u is just the relative velocity between frames. And that is great. That's consistent with how we know how to shift between coordinate frames, right? So we're going to have our time as well equal to some gamma factor times the time minus ux over c squared. We got the x there because we're moving in the x direction, right? And if we wanted to consider the special case, the transverse transformation, well, what is that? We're just going to have y prime equals y, right? That is what we're going to be focused on for the purposes of our demonstration here, right? So in that sense, we're going to be just looking at that, so we don't need to account for the parallel direction, the x-axis. So we're going to change that to y. Now, we're going to take the ratio between both of these equations and then add another part where we just take the instantaneous rate of change, right? So what that gives us now, well, we're obviously not going to be using this because we're looking at the special case. So we're going to look at the transverse change in velocity, right? So we're going to have dy prime is equal to, well, just dy, right? We have dy, and that we're obviously also going to be dividing it by our time variable. So we're going to have dt prime, which is equal to our gamma factor, gamma times dt minus u dy over c squared. Okay? Now, what we're going to do is we're going to multiply the numerator and the denominator by 1 over dt, right? So 1 over dt times 1 over dt, okay? And what that gives us is this divided by this just gives us our instantaneous velocity in the y direction. So that's just v prime sub y is equal to dy over dt, right? So that is also going to be our instantaneous velocity in the non-primed frame. So we're going to have v sub y over our gamma term, and that dt is going to cancel with that, just become 1. So we're just going to get 1 minus u v sub y over c squared. Now I'm going to leave this as an exercise to the viewer, and I know people hate that, but it's messy, and we're going to be looking at it from a different angle. But this is effectively the reason why momentum conservation is not upheld when we're trying to shift between frames here. We won't have a particular invariance that occurs between both frames. If you try to transform these, you end up with an issue due to these denominators here. You just can't add them. There's just no reconciling these ideas, unfortunately. So this is the issue you run into. If you want to try it, by all means, just work out the initial momentum of both particular frames and then the post or the final momentum in both frames, and you'll see that you will not be able to uphold momentum conservation when considering just this. So that suggests that we need an alternate explanation and a correction to account for this momentum change here. Okay, so I'm going to get rid of this, and we're going to shift our thought experiment over to this side and expand upon these ideas here. So bring your eyes over to this side of the whiteboard, and you can see that we are now considering two different frames, not simply just the Earth frame, to make our case such that we need, or to make our case for the fact that we need a new update for our momentum equation. So to make that case, we're obviously looking at our Earth frame before the collision, whereby we have this set up such that the magnitude of the y spatial coordinates are equivalent. Obviously not to scale, but we're constructing it to ensure a little bit of simplicity and to negate any sort of natural messiness that might occur when trying to consider some disproportionate spatial coordinates. So it just makes this thought experiment far simpler. And where it's already abstract enough as it is, let's keep it as simple as possible. All right, so we have ourselves our fast-moving proton ejected from our supernova coming into collision at event 0 here. So we have 1 representing the event of the fast-moving proton, and 0 the collision at which it ends up at its destination, where it collides with the slow-moving proton ejected from the stationary observers on Earth. Now, we have this spatial coordinate represented as 1 meter, so naturally, because these two y coordinates are equivalent, they're both 1 meter. So this geometry is going to ensure that simplicity here. Now, when we move on to a separate frame of reference, where now we have a rocket moving in the x direction, well, the rocket is moving at such a speed such that the events 1 and 0 are shifted vertically with respect to the collision now. So now, instead of the stationary observers seeing that the proton is moving over this long distance at this sort of hypotenuse angle, well, from the rocket's frame, now it appears such that events 1 and 0 are now perpendicular to the collision point. Now, this is where the difference in observations come to play here, or the idea of simultaneity, whereby both observers are going to disagree on the order of these events, right? So to account for that, we have to look at not just their measured time, because they're going to disagree, and we're not going to have momentum conservation upheld, and that is a problem. But what they will agree on, what both observers will always agree on, is the proper time, the wristwatch time of each individual proton. Even though the events are flipped relative to their frames, they will always agree on at least one thing, and that is the proper time. And the proper time is the key idea when starting to develop some of these ideas and these correction factors. So the proper time we can represent with as tau from 1 to 0 1 to 0. So event 1 to 0 is equal to tau from 2 to 0. So tau from 2 to 0, these are equivalent. That's all fine and good. Perfect. This is always true between frames. Both frames, this is always going to be the same. Now, there's another observation that we can also make. Because we're talking about the proper time for both, well, there is some equivalence between the proper time of the slow-moving proton and its measured time. Those are going to be effectively the same thing because they're not experiencing any relativistic dilation or any factors or length contraction or anything like that. That is the overarching idea when trying to consider these sort of different sort of spatial coordinates and time variables. That is basically to say that we have our proper time of 2 to 0 is approximately equal to the measured time of the Earth frame, because it's always going to be about 1 second anyways. Even if there is a difference in relativistic factors here, it's practically negligible, if not so. So we're going to have t20. These are going to be about the same. So in that sense, we can write out our momentum for the transverse direction. So if we were to do that, we would have m times y over tau from 2 to 0 is equal to the mass times the y coordinate over the measured time from the slow-moving frame. Now, this is frame dependent. This is not. If we were to write out the frame independent version of this, it would just look like that. So we would just have m tau, sorry. So we would just have my over tau from 1 to 0 is equal to minus. So remember, we're changing directions, so we have to adjust the difference in direction by incorporating this negative sign here due to its elastic collision nature. So we're going to have my over tau from 2 to 0. So this is our frame independent version, and don't forget the negative. This is our frame independent. It is only true within the Earth's frame, and that is where we can see the problem that would occur if we were considering a non-proper time sort of idea. If we were considering the measured time within this frame, well, we would have clearly some discrepancies, because if we just plugged in the measured time in for the proper time of the fast-moving proton, well, then you're going to see some differences, some enormous differences, because obviously the time at which it took to go from 1 to 0 from the Earth's frame's perspective, well, that's 10 million years or something of the sort of 350 million seconds. So obviously a huge issue that we need to correct for. And that should hopefully express why we need to update this equation. So within that sense, since we are considering simply the wristwatch time of the protons, let's incorporate our proper time according to this particular idea. So we're going to have now our momentum, and we're going to write this in vector form. So our momentum is going to be equal to m times dr over dt prime, because this is obviously not the variation at which we would be considering the proper time, because obviously we haven't represented it with our tau here, right? Well, what is tau? What is the proper time, like effectively speaking? So if you recall from my last video, I briefly went over time dilation, and time dilation is represented as so. So we're going to have t prime is equal to tau over our square root of 1 minus b squared over c squared, or simply just our gamma factor times tau, right? So if we take the instantaneous sort of rate of change here for both times and then rearrange it, we can see how we can sort of add these factors in for our new equation. So since we're considering the proper time, well, let's rearrange this and then see how we can update the equation. So we're going to have dt prime, and if we wanted to bring that over, we're going to have that over d tau is equal to, well, 1 over this, that's gamma, so we're going to have gamma, right? So let's multiply our new momentum, or our old momentum equation by this ratio right here. So we're going to have that times dt prime over d tau. And what is that? We've already established what that is. You can see that when we substitute this form in for our old equation, this ends up just becoming gamma. Therefore we just have our new momentum equals mv gamma. Okay? And this is our new momentum equation, and that is a key idea in developing E equals mc squared, right? Because naturally, when you start developing notions of momentum and updated equations from the old sort of Newtonian standpoint, well, you have to start considering a new form of force. Because if maybe you recall, the idea of force, or the definition of force, is simply just the instantaneous rate of change of our momentum, right? Because if you recall, we have our force is equal to dp over dt. But that's within the old Newtonian standpoint, if we just considered p to be m times v. So if we wanted to plug this factor in here, we would have to go into a little bit of calculus and see what that ends up providing us with, okay? Now, it's worth noting that since this is just simply equal to ma, well, we're also considering the orientation between the vectors, or the orthogonality between the force and its acceleration. Because if we were simply to consider an orthogonal standpoint between the force and the acceleration, well, that would mean within the context that we're describing, the particle of interest would be deflected in a circle. Therefore, our gamma factor would just be treated as a constant. We're not going to be doing that. We're treating it such that it is following a parallel path along the x-axis. So that is the idea we're going to be employing first when deriving our new form of force here. So we're only considering the parallel direction, the linear direction, and the force and the acceleration are essentially pointing in the same direction, okay? So that's what we're looking at. So to do that, we need to now use some calculus, okay? So we're gonna have force is equal to, what do we have here? So plugging in our new updated momentum, we're gonna have d times gamma mv, right? Times d over dt. Okay, so we just need to use a little bit of product rule and a little bit of chain rule. So we're gonna have our force is equal to so we're gonna have the mass times velocity times the derivative of our gamma factor. So we're gonna have mv times d gamma over dt, and that is gonna be plus our gamma factor times d mv, do that there, over dt. Okay, now fortunately our mass is a constant that will be pulled out of our derivative, and all we really need to work on, at least focusing on this particular side, is dv over dt, which is just the acceleration. Now this is where we have to use chain rule. So we're going to have mv, and for our gamma factor, and we're just going to bring this up to the numerator. So we're going to have d times 1 minus v squared over c squared over raised to the negative 1/2, over dt plus gamma ma. because remember, dv over dt is just our acceleration, okay? Now, let's bring this down, use the chain rule, and then start working this through. So we're going to have mv vector, where we have our negative 1/2 times 1 minus b squared over c squared, so the negative 3/2 times, times 2v minus 2v over c squared times dv over dt plus gamma ma. All right, this looks a little bit messy, but we will clean it up. So we're going to bring this over here. These negatives are going to cancel along with the 2's, okay? And we can bring that velocity over here, and then it just becomes v squared over c squared, okay? And at the same time, we're going to be factoring out gamma ma too, all right? So let's do that. So over here, we're going to have our gamma ma, where now we have these cancel, and we have this, so we have v squared over c squared over, remember we're factoring out a gamma, so this just becomes 1 minus v squared over c squared raised to the 1 plus 1 here. Okay, so that works out perfectly. There's a vector here. Okay, so now we just got to find a common denominator and add these together. So what we got here is gamma ma, where we have 1 minus v squared over c squared, and we have v squared over c squared plus 1 minus v squared over c squared. Okay, if we were to just bring these over, these would end up canceling, and we just have gamma ma 1 over 1 minus v squared over c squared, which, if we just multiply with our existing gamma factor, is simply just our new force. So force is equal to gamma cubed times ma. And I don't know about you, but I find that pretty amazing, the fact that such a sacred tenet of the Newtonian viewpoint, that paradigm has been just such long-standing and very cherished. And it shows you that it is obviously a very good approximation until you start considering faster and faster speeds and objects that are accelerating. You need some sort of restriction to impose upon any body moving close to that point, so you can account for any sort of force in that sense. And that's very useful when considering small particles with very little mass. Okay, so now we have ourselves a new variation of force that suggests that we need to start considering a lot more. And what I mean by that is the work energy theorem was a very useful idea when relating the work you need to have basically in a particular system that is equivalent to our kinetic energy. So when we're talking about the work energy theorem, we need a new idea, because if you recall from my last video, the work energy theorem is just the network equals some integral from position to initial position to final position, which is the force times the direction at which the object of interest is placed here. So we are going to have to go through that derivation again. We're going to use some of the same rules, but we're going to end up with a different result, obviously. So in that sense, we're going to clear this off, and we're going to rework the work energy theorem. Okay, so we have our new force, and we have our old work energy theorem, which says that we have the network equal to the change in kinetic energy, right? And I put a little question mark over that just because, is that really what it equals now when considering the Einsteinian paradigm? Well, it's not really all that clear until we work it through, obviously. So let's pretty much go through the same sort of process that we went through in the previous video, which I'll link in the description down below. So what we have now is a work, right? Considering the network, where we have some integral from our initial position to our final. So we're going to call that R initial and then R final, times some force, which we're going to be plugging in as gamma cubed MA. So we're going to have gamma cubed M times A times some limit of integration with this, which is of course our position, right? So we're going to have dr, right? Which we're going to be dotting between, because obviously what we end up with is supposed to be a scalar, okay? So now what we need to do is realize that obviously the acceleration is just the differential in velocity, the dv over dt. So we're going to have some integral from r initial to r final, to r final times gamma cubed times m dv over dt, okay? Times our limit of integration, which is just our position that we're moving along, okay? All right, so let's bring this over and look at a particular substitution that we can make, which may be familiar to any of you who watched the previous video. So we're just going to have dv over dt is equal to dv over dr times dr over dt. Great. You can see how this is identical to this. If you just do like the cross cancellation here between our positions, so that ends up giving us the same thing. Therefore, we can just substitute that in because it's equivalent. So now we're going to have some integral. I'm going to wait on the limits here. So we're going to have gamma cubed times the mass, where we have our dv now over dr times dr over dt times dr. Okay, great. So now you can pretty clearly see that we can now just cancel these, but we're going to bring our dr in because we're just doing a little change of variable, which will naturally require us to change our limits of integration as well. Okay, so what do we have? So we're going to have our integral from, now we're focusing on the limits for our velocity. We're starting at some velocity at which is 0 to some arbitrary value, right? So that's what we're going to be starting at. So 0 to v, where we have gamma cubed m times dr over dt times dv. And of course, dr over dt is just our velocity. Okay, so we're going to take this, bring it over here, and then solve it. Okay, we're going to have our integral from 0 to v. We have gamma cubed times the mass times our velocity dv, right? Okay, so now we can actually start making some useful substitutions and taking the indefinite integral. Okay, so what is gamma cubed? We're gonna expand that out here. We're gonna have our integral from 0 to v, where we have, I'm gonna pull that m out because that's a constant, and we're gonna have v dv over our square root, oh sorry, not a square root, over our 1 minus v squared over c squared raised to the 3 halves. Okay, so we're gonna do a u substitution here. We're gonna have u is equal to 1 minus v squared over c squared. Okay, take the derivative. We got du equals our minus 2v over c squared, 2v over c squared dv. And now what we can do is bring that c squared over along with the 2. That way we can substitute in for our dv. So we're going to have v dv is equal to minus c squared over 2 du. Okay, so now we can substitute that in, and it's going to be a pretty simple integral to take now. So we're going to have, I'm going to bring these constants out as well, and you'll start to see something very familiar. So we're going to have minus mc squared over 2 times the integral from 0 to v of, we just have du, and then we're going to bring this up to the numerator. We're just going to have u raised to the negative 3 halves times du. All right. Now we can just use the power rule, where simply we just take this times plus 1, which is just going to be 1/2, divided by 1/2, which is going to be 2u to the negative 1/2. So we're going to have minus mc squared over 2, where we have our indefinite integral with our limits from 0 to b of minus 2 times u to the minus 1/2. All right, so now we can substitute our u in now, which was obviously this, and we can bring that out and cancel these two. So we're going to have mc squared, where we now have from 0 to b of 1 over the square root of 1 minus b squared over c squared. All right, great. So now we can take the limits, and what that gives us is this factor minus some 1 minus b squared over c squared, which is just 1, right? So we're going to have this over here. So mc squared, where we now have our 1 over the square root of 1 minus b squared over c squared minus, well, what do we got? We got minus 1, right? Because this obviously is going to be 0 over c squared, and 1 minus 0, take the square root of 1, which is 1, so we just got 1. So 1, and there we go. So what does that give us? Well, this gives us our new equation. So we're going to have now m, so we're going to call it gamma mc squared minus mc squared is equal to none other than, yes, our work, but is of course also equal to our kinetic energy, right? Times our change in kinetic energy. And we can rearrange this a bit to clean it up, because the full equation in its full glory is simply just gamma times mc squared is equal to the change in kinetic energy, change in kinetic energy plus mc squared. And that might not be the form you're used to if you haven't been formally introduced to mc squared. Equals mc squared is just this part. And what is that part? Well, the way Einstein interpreted this result is that this factor here represents the total energy, the energy of a system. And then we obviously have our kinetic energy, which represents the body in motion. And then we have something else, our rest energy. That is what this is defined as. So we can rewrite this. I know I'm running out of room, but we can write this as our E total is equal to our change in kinetic energy plus our rest energy. Now, it might seem a little absurd to suggest that somehow kinetic energy has any sort of relationship between the two. And I can very clearly demonstrate that by performing an expansion. And that is what we're going to do here. And we're just going to validate this idea real quick. So let's take a look at this new form of energy we've just derived and see how it expands using what's known as the binomial expansion. And if you're not familiar with it, I'll do a quick little demonstration as to what that is, and then we'll actually employ it. Okay, so we're going to have our binomial expansion, which says that we have some 1 minus x term raised to some n value is equal to 1 plus n, is equal to 1 plus n times x plus n times n minus 1 over, or n minus 1 times x squared over 2 factorial, right? And we're going to, x squared is just by itself. And then we're going to add that to n. My God, I keep writing n. M. So we're going to have n times n minus 1 times n minus 2 over 3 factorial times x cubed. And that goes on forever. That is the idea, the basic idea of what a binomial expansion looks like, which within the context we're trying to analyze it, right? Now, there's a more general form, if maybe you're more comfortable with it, but this is simply equivalent to our sum of some k value equal to 0, where we have some n here, and that is going to be using some combinatorics where we have n choose k times a raised to the n minus k times b to the k. Okay? And this factor here is pretty much what we just wrote out, where n over k is just equal to n times n minus 1 times n minus 2 times where we have just n minus k over k factorial. So that's how we're going to be analyzing this term here. We're using this, we're going to expand and see what these successive terms end up yielding us. So, now, we know that gamma is just 1 over the square root of 1 minus b squared over c squared. So we can write mc squared. We have 1 minus b squared over c squared raised to the negative 1/2. And this form here, this v squared over c squared, let's just simplify it even further so we don't have to deal with this annoying fraction. Well, we're just going to have beta equals v over c, right? So we can rewrite this as just mc squared 1 minus beta squared negative 1/2. All right, so now we can expand it fairly easily. So what do we get? Well, we got our 1. So 1 plus our n value. What is n? Well, n is just this. So we're going to have plus negative 1/2 times our x, which is our beta here, which is just minus beta, right? So we're just going to have our times minus beta squared here, right? And we can move further, and we just have that plus our n minus 1/2 times, now we're moving up a term, so therefore we have to include n minus 1, which is just negative 1/2 minus 1, which is minus 3 over 2, so minus 3 over 2, and that is going to be over 2 factorial, where we now have negative beta squared, right? All right, so let's simplify this a bit, and what we're going to have is mc squared times our expanded polynomial, where we have 1 plus, these negatives cancel, so we're just going to have 1 over 2. Beta squared is just this, so we're going to have, and since the negatives go away, so we're just going to have b squared over c squared plus, these terms will multiply. We just get 3 over 4, and we multiply that by 4, we get 3 over 8 plus 3 over 8 times negative beta squared, which is just b to to the fourth power over c to the fourth power plus dot 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 dot. Higher order terms, getting closer and closer to 1, they start to become negligible, not worth considering. However, if we distribute this across, well, what does that give us? Our total energy is just simply equal to mc squared plus these c factors are going to cancel. And what are we left with? We're left with 1/2 mv squared. What is that? That is the kinetic energy. That shows that there is a deep relationship between the kinetic energy and this total energy term and this other new form of energy, which is simply the rest energy, which suggests a very earth-shattering idea that gave rise to a lot of very horrendous results because people sort of exploited it for their own gain and used these ideas for war. But the idea is that the rest energy means that even a body that is not in motion has reserves of energy, not just reserves of tepid energy, but reserves of energy that is enormous because of this c squared, meaning the threshold energy value of a system is always going to be at its peak when you are in this center of momentum frame, this rest frame, which suggests that there is more energy when a set of particles, an ensemble of particles, are at rest with respect to one another. And that will give you an enormous surge of energy, and is primarily why these ideas have been so devastating to humanity, at least those who saw it in their best interest to exploit it for some frivolous notion of war. I don't mean to be a bummer now, but that being said, I think these ideas are incredibly fascinating, and I hope you learned something today.